Hello, Medford community. I'm Brett Champion, the proud superintendent of schools here in the Medford School District. And welcome to Medford Anywhere Learning TV. We are so grateful to our partners who helped us bring Medford Anywhere Learning TV to life. And those include Southern Oregon PBS, KTVL, KDRV, and the Dove TV. Special shout out to Southern Oregon PBS for also producing these parts. In the Medford School District, we believe that all are learning, and learning is for all. And what better venue to share our learning than Medford Anywhere Learning TV. Welcome.
Oh, hi there. Hey, I'm having some science fun with my Newton's cradle. This is a great example of the law of conservation of momentum. Also, it illustrates how potential and kinetic energy are related. So if you don't know about that law or those terms, then don't worry, because on today's episode of Science Rewind, we'll learn about those very concepts and probably a few surprises along the way. So sit back, get ready, and let's go in 3, 2, 1.
Go!
Welcome to today's episode of Science Rewind, where I rewind the science for you. Today's topic is the conservation of momentum and how do Newton's 3 laws of motion interact with momentum. Well, if you recall at the beginning of our episode, I showed you how Newton's cradle is a great example of the conservation of momentum. It really speaks to Newton's third law, which states that for every action there is an equal and opposite reaction. What does that mean? Well, let's take a look.
As we look closer at the Newton's cradle, we can see the 5 balls in motion. Momentum can be defined as mass in motion. All objects have mass, so if an object is moving, then it has momentum. The formula to measure momentum is mass times velocity. When you multiply mass and velocity, the end product is momentum. As each outside ball strikes the center balls, momentum is being conserved. When the outside ball is at its peak arc, that's when it has maximum potential energy and the least amount of kinetic energy. As the ball continues downward and strikes the center balls, it is then at its maximum kinetic energy and its least potential energy. The mass of each of the balls doesn't change, and the velocity of one ball hitting another keeps the same momentum, which is being conserved. When we say that momentum is being conserved, it means that as the balls move, energy is transferred from one ball to the next, and no momentum is lost in the process. Eventually, the kinetic energy is transferred into the table as sound and thermal energy. Over time, friction will slow the balls until they stop. The Newton's cradle is a great example of the conservation of momentum.
Well, we're in the gym now, and joining me are 2 special guests, my daughter Maddie.
Hi there.
And my son Ben.
Hi, everyone.
So they're going to help me show you how conservation of momentum works in a vertical display. But before we talk about that, though, we have to talk about potential and kinetic energy. So pop quiz time, Maddie, what's potential energy?
Well, I'm pretty sure potential energy is stored energy.
Yeah, that's great. And Ben, what is kinetic energy?
Kinetic energy is energy of an object in motion.
That's great. Makes a science dad proud. Now, here's the thing about that. I know that these three balls are different in size or mass. Ben's basketball, my dodgeball, and Maddie's tennis ball. The question, though, is this, is if we drop them from the same height at the same velocity, which ball will bounce up higher after it hits the ground? Now, remember, we're talking about conservation of momentum, and when the ball hits the ground, it's going to transfer its energy into the ground and bounce back up. So let's ask Ben. Ben, what do you think?
I think my ball is going to bounce the highest. I mean, it's a basketball.
Okay.
It's designed to bounce high.
Okay, and Maddie?
Well, mine is really small and doesn't weigh as much. So I'm pretty sure this one will go pretty high.
Yeah, it could. Well, this is a dodgeball, and I know these can bounce really high. So I'm thinking that my ball will actually bounce higher than your two balls, the basketball or the tennis ball. So let's find out. Let's drop them and see which one has more kinetic energy. So we'll count down. We'll go 3, 2, 1. We'll drop the ball. You guys ready for this?
Yes.
Let's do this. Here we go. Okay, on 1. Ready? 3, 2, 1. All right. So which ball bounced the highest?
I think the kickball bounced higher, but I'm not sure.
What do you think?
Mine didn't bounce very high.
Yeah, well, I think the kickball was actually higher, but you know what we need to do is a science rewind.
The balls were dropped from about 4.5 feet. Even though they didn't start from the exact same height, we can see that the kickball had more kinetic energy because of the material of the ball. In fact, kinetic energy is directly proportional to mass. The basketball has more mass, but the kickball hit the floor with greater elastic energy. The tennis ball had the least amount of kinetic energy because of its smaller mass.
So how can we increase the kinetic energy in the three balls? Well, there's this thing called the Galilean cannon, which is a famous experiment that Galileo did with 2 balls. It can also be done with 3 balls. But what he showed was that the energy is being transferred or conserved in the balls and going from one ball to the other. So come on in closer, guys, and we'll show how this is. So we know the basketball it feels like it has more weight and more mass. The kickball has a little bit less mass, but it's more bouncy, the material. So you hold that. And the tennis ball is definitely smaller, less mass, but a little bit harder, more compact. So my question is, if we drop all 3 balls at the same time, okay, you might want to back away a little bit, guys. What's going to happen with the 3 balls? So let's find out. Ready? Here we go. 3, 2, 1. Whoa! Did you catch that? Let's rewind that and watch it again.
As the 3 balls are dropped, the basketball and kickball are transferring their kinetic energy into the tennis ball. The kickball acts as a trampoline for the tennis ball as it slams against the basketball. All of that force helps to propel the tennis ball into the air. This is an example of the conservation of linear momentum. The mass of each ball stays the same, so the velocity increases, and that's why the tennis ball takes off like a rocket.
So now we come to Newton's second law of motion, which states that force equals mass times acceleration. Well, what does that mean exactly? Well, think of it this way. I have a ping pong ball and a golf ball. Which one has more mass? The golf ball does. So if I use the same amount of force on both of the balls, which one would accelerate faster? Let's see. So here's the ping pong ball. It's pretty fast. It goes right off of the table. Now here's the golf ball. Same force, but slower acceleration. So what does that mean? Well, that means that if we look at it in a different way, that acceleration really equals force over mass, meaning that the acceleration will happen at a faster or slower rate because of the mass of the ball or the object. Let me show you in a different way here. So here I have a turkey baster handle and a ping pong ball. And I'm going to go ahead and just use regular force with my hand to accelerate the ball out of the baster. So watch what happens. It went pretty far, about 4 or 5 feet. Thank you. And thank you. Now let's try it again, but let's use a chemical reaction or explosion to make the ball go farther. So the force will change. The force will be greater. Glasses and safety as always. So here I have a little sparker, as you can see. And by the way, don't try this at home. And I'm going to put this inside of the baster. And I'm going to spray a little bit of Bianca. Pretty good. Mouth spray in here. And that's, of course, alcohol. And I'm going to go ahead and put the ping pong ball in. Now, I'm going to increase the force that's coming out of this baster to propel the ping pong ball out of it. So if we go back to Newton's second law again, acceleration equals force over mass. So I'm going to increase the acceleration because I'm increasing the force. The mass is the same. Let's watch what happens. Ready? Okay, here we go. On 3, 2, 1. So as you can see, we increase the force of the ball as it propels out with an explosion. And so the acceleration was greater. The mass was the same. But let's do this on a bigger scale. Let me call my friend Steve really quick. And he's a science teacher. Hold on.
Hello?
Yeah. Hi, Steve. It's Greg. Hey, can you bring over your cannon that you have?
I think I could.
Awesome. Okay. Yeah, I'm going to talk about Newton's second law of motion.
But what is...
Great. All right. I'll see you there. See you there. So joining me right now today is my friend Steve Holst, who is a science teacher. And Steve, you brought some gadgets with you to help illustrate Newton's second law of motion.
I did, Greg. I brought a couple. I thought we'd have some fun with it, okay?
Sounds great to me.
All right. So first thing we'll try is this. I call it a tennis ball cannon. And so you'll see how it works. But Newton's second law says that force equals mass times acceleration. So what we need to do is apply some force to the tennis ball and get it to accelerate. Okay. And of course, the law says that the mass is important. The bigger the mass, the acceleration goes down.
Okay.
Right?
Right.
Okay. So we're going to try, I'm going to try to do one more thing too. I'm going to try to vary the force with this here. Okay. So I have a fuel. My fuel is, believe it or not, is going to be propane.
Propane.
And I'm going to try putting different amounts of propane in here to find out what happens to the acceleration when we change the force.
Okay. Sounds great. Well, let's do it.
Let's do it.
Okay.
As Steve prepares to fire the tennis cannon, he carefully loads the barrel, pushing the tennis ball about a third of the way down. He's careful to leave enough space so the gas can expand after ignition. For the first test run, Steve will be using a 4-second burst of propane.
So we have a sparker on the other side. The sparker here is going to, when I push this red button, it's going to go ahead and spark the propane gas, which is flammable, and create a force, which is going to accelerate our mass, which is the tennis ball. Here we go. 5, 4, 3, 2, 1.
As you can see in the slow motion replay, the force that propelled the tennis ball out of the barrel of the cannon was so great that the tennis ball hit the far wall and bounced all the way back past Steve.
All right, so that went pretty far. We had good acceleration that time. Let's try changing one factor. We're going to change not the mass. The mass will be the same. We use the same tennis ball. But this time, we're going to try changing the force and see what that happens to the acceleration. So instead of using 4 seconds of propane, this time we're just going to try 2 seconds and see what happens. All right? You ready to give it a shot? Let's try it. Here we go. 1, 2. Okay. And then we'll fire this away and see what happens. Okay? Here we go. 5, 4, 3, 2, 1. A lot less force. Excuse me. A lot less acceleration that time when we had a less force. Do you guys agree?
Steve was right. By only using half the amount of propane in the tennis cannon, the acceleration was cut in half, resulting in the tennis ball bouncing back to the half-court line. Less force does equal less acceleration. Newton was right. This time Steve is using a bigger cannon. The fuel, not propane, but isopropyl alcohol. The perfect fuel for a larger explosion. And according to plan, the first test fire goes off without a hitch. The soft foam ball accelerates across the gym diagonally with greater acceleration.
Nerf ball fired pretty well. What would happen if we tried a wiffle ball or this toy soccer ball here? Let's go ahead and give that a shot and find out. All right, this time we've got the soccer ball in here. Let's see what happens.
But things don't always go according to plan. After a couple of misfires, Steve has to air out the barrel of unspent fuel. No such luck. I guess it's back to the drawing board.
Well, Steve, that was a lot of fun. Thanks for coming today and showing us how Newton's second law of motion works.
My pleasure, Greg.
Maddie, I understand that you know a lot about Newton's first law of motion. What does that first law state?
Well, it states that an object in motion will continue to stay in motion and an object at rest will continue to stay at rest unless interacted by an outside force.
So if I have it right, I imagine myself as an astronaut working outside of the International Space Station, and I'm trying to go from one part of the station to another, and so I propel myself with my own mass and my own velocity going through space because of momentum. I'm going to eventually continue, unless I can find a handhold or hit part of the station, I'm going to continue to go in space, right?
That's right. That's usually why they're attached to the space station.
That's right, with
so
a tether.
Yeah.
Yeah. So my question then is this: how can we show the viewers the first law if we don't have a space station here? We can't go up
Well,
to do that.
I brought something along that is a little more our budget.
Okay.
It is a beaker full of beads, and you'll notice these beads are one continuous long strand.
Okay.
So they're all attached to each other, and I am going to drop it outside of the beaker, and if Newton's first law is correct, it should travel continuously until it hits the ground, which will be the outside force.
Right, okay. Well, it's not very far from the top of this beaker to the tabletop, so how are we going to show it?
I thought I'd bring a stool here, and then we can make the drop even higher.
Okay.
And this will also play a part in our experiment.
Okay, so what's the purpose of having a higher height for the bead drop?
Well, I'm hoping when the beads drop, it will have a farther way to go, so it will pick up more momentum and everything, and you're going to see a curve happen up top here.
Oh, like a little arch?
A little arch, yeah.
Okay, well this sounds a lot like inertia, and you talked about momentum, so the momentum of the beads going over the cup because of the inertia should make it go pretty fast.
We're hoping so, yeah.
Okay, so can I hold it?
Yes, please.
Okay, I'll move over this way.
Okay, should we count down?
That's a great idea. Ready?
Ready?
3, 2, 1. Ooh, look at that. That is amazing, Maddie. Look at that arch.
Yeah, it's pretty cool.
Wow, so what just happened?
Well, we just demonstrated what is called the mold effect here.
Okay.
And so what happened was it continued going like I thought it would, which proves that Newton's first law does exist.
Mm-hmm. So as the beads were pushing against the bottom of the cup was pushing up against the beads. And I think, if I'm not incorrect, the mold effect talks about how as the beads go over, the momentum is just enough because of Newton's third law to push, to create the force to push back to make that bead go over the top of the cup.
That's right.
That's awesome.
Newton's third law is for every action there's an equal and opposite reaction, so we could see also that how that went into play, like you said.
Okay, so how can we make that arch more pronounced or bigger?
Well, I feel like height really plays a good role in that, and so I'm hoping if we put it at a higher height, we will see a bigger arch.
So let me ask you this. If we go to a higher elevation, would the arch be bigger?
What do you think?
Hey, I'm pretty good.
Hey, what are you doing there?
Oh, hey, Ben, I have the best magic trick for you. Okay, now watch. Guess which hand the coin is in. Ready? Yeah, that's right. Okay. Well, do you have a trick that's more impressive than that trick?
Actually, I do. So, I have here a glass,
Okay.
a paper plate on top,
Yeah.
and then plastic container and a tennis ball.
Okay. And what do you have planned for this demonstration here?
Well, I thought this would help us demonstrate the concept of inertia.
Oh, Newton's first law of motion.
Yeah.
Excellent. So how does this work?
Well, so I'm going to hit this paper plate here. Do you think that that I can just hit this paper plate and that this tennis ball will drop into the glass below?
Straight down. Let me see here.
Without touching the tennis ball.
Without touching the tennis ball, just the plate. You know, Ben, I think that's scientifically impossible.
Well,
Yeah.
watch and see.
Okay.
All right, on the count of 3, I'm going to hit this paper plate. 1, 2, 3.
That is pretty impressive, actually. So, inertia caused the ball to go down into the cup. How does that work?
That's right. So the tennis ball had inertia, so it wanted to stay at rest.
Yeah.
So I hit the paper plate and caused that to move out of the way when I
Okay.
applied a force to it.
Oh.
But the tennis ball didn't have the force applied to it, so it just was affected by gravity. It wanted to
Right.
go straight down into
Right.
the glass below.
So the object, the tennis ball wanted to go straight down because the gravity force was straight. Okay, got it. So that makes sense to me, but that's pretty impressive. Do you have anything else that's even more impressive or just as impressive?
Well, I do have this funny looking thing.
Okay, what's that?
Well, it's called an inertia hat.
Okay,
So
how's it work?
let's try it out and see.
I have to wear it? Okay, so what's the point of the two balls?
Well, if we apply a force to the balls,
Yeah. Oh.
they stay in motion because of Newton's first law.
Oh, that's right. Well, my head's like the sun and these are like planets. And I'm guessing that being bald helps with the friction part. Cool. So if I move around, what will happen with the two balls?
Well, hopefully, if they'll stay at rest,
Yeah.
when you move around, the balls will continue to stay at rest and they won't move with your head.
Okay, let's find out if that's true. Ready? Here we go. Yeah, I'm gonna go ahead and rotate around. Whoops! Oh, so you gotta put it on top of my head here, make sure it stays. All right. Try this again. This is science, it's not always perfect. And so I'm moving around.
Yeah.
Hey, it works out pretty well. That's cool. So Newton's first law says, again, what?
An object in motion tends to stay at motion, and an object at rest will tend to stay at rest.
That is cool. So inertia and friction kind of go hand in hand, it sounds like.
Yeah, so the first law is basically talking about inertia.
Yeah.
Because the balls have inertia, they want to stay in motion if they're in motion, and they want to stay at rest if they're at rest. But friction can stop that. So
Yeah.
the reason the balls eventually stop is because of friction with
Okay.
that point of contact on your head.
Well, can somebody make this at home, you think?
Yeah, it's actually really easy.
Okay, well, show us
So
how.
you just use a coat hanger
Okay.
and make sure you get your parents' permission before grabbing one of these.
Okay.
But you'll straighten this out completely as
Yeah.
much as you can, and then fold it in half. And then you'll take the two ends here and bend them in like this.
Okay.
And then
So
you
it's,
just
it's like an M.
yeah,
Yeah.
like an M shape. Yeah.
Okay.
And then you need to have foam balls or something to
Okay.
attach to the ends.
Okay, that
And
makes
this
sense.
provides a little bit of mass.
Okay.
So Let's see.
And it just
here.
goes in. So I think if these balls were heavier, it'd probably be heavier on your head, right? So the lighter the better, probably.
Yeah.
That's great. Okay. And then should I just try to see if this works, if it's balanced?
We'll see.
Okay. Let's see here. No, it feels like it's a little bit to the side.
Yeah. So it may not be balanced the first time.
Okay.
So you have to balance it in your hand and adjust
okay.
parts of the wire to see if you can get it to balance.
Got it.
Yeah.
Well, Ben, thanks a lot for showing us Newton's first law and inertia. And this has definitely been a fun experiment for me. Yeah, so try this at home. Try the inertia hat and also try this experiment too. And see if it works. Thanks, Ben.
Yeah, you're welcome.
Well, that wraps up this episode of Science Rewind, where I rewind the science for you. Today's topic was the conservation of momentum and also how does Newton's 3 laws of motion affect momentum. Hopefully you learned something new today and had fun while you were watching. If you want to email me at the address below, you can ask a science question or a comment, and I'll try to answer it for you on air. In fact, we have one now from, let me see here, little Jimmy Van Heusen, a 3rd grader, and he asks this question. Mr. Franklin, what is Planck's constant? Jimmy, that's a great question. Hold on. Hey Siri, what's Planck's constant?
Here's some information.
Yeah, you know, Jimmy, that's a big topic. So we'll cover that in the next episode. We'll answer your question for sure. But please email me, ask questions that I can answer that are interesting to you. And I'll try to hopefully educate you on things that you're asking. So anyway, that wraps up this episode. I hope you had a great time watching and learned something. So as always, stay healthy, stay learning, and we'll catch you next time on Science Rewind.
You still watching? Good for you. They ought to really market these things.
Thank you for joining us today on Medford Anywhere Learning TV for the latest updates on what's going on in the Medford School District, including COVID-19 updates as well as next steps for Medford Anywhere Learning, because there's always more still to come. Check out our website at www.medford.k12.or.us. See you soon.
Actually, I made this like in 2011. It's fun. It's a cool hobby. So this is just my wax cart that I use every summer. I've done all this on my own time. I just took an old custodial cart and transformed it into something easy so I can have everything. When I'm at each classroom, I'll have everything I need, because I like to make it convenient for anyone.
Ted kind of embodies the Black Tornado Pride, our BTP, and he customizes his carts and paints them all up in the red and black and does that cool stuff.
Besides making carts, I do clean around the school too. So, I'm out in the field cleaning the bathrooms and the track, the baseball bathrooms, collecting all the trash around the campus. Yeah, oh, it makes me feel good that I did a good job, and I feel that everything's gone smoothly.
Ted is such a positive force on this campus. He's always there for anything anybody needs, and no order is too tall or no request is too wide. The guy will get it done.